I'd like to introduce Scott Wisdom. He is a researcher at Google in doing sound separation and related activities. He's going to talk about unsupervised sound separation, a new paradigm for audio processing. Scott got his PhD at UW, and he spent some time working with me and Jonathan at Merle as an intern. He also worked at Microsoft Research and Affectiva before he joined Google. Take it away, Scott.
Thanks so much for the intro, John. Yeah, I'm going to talk about unsupervised sound separation, how it is a new paradigm for audio processing. And I've had the privilege of collaborating with a lot of talented people who are up here. There's too many names to go through, but yeah, I really am grateful to have been able to work with all these great folks. To talk about the task that we're going to discuss today, this is the basic setup for sound separation. We take an audio mixture and run that into a separation model, and that produces some number of estimated sounds. And we have 3 outputs here. Something I've been thinking about is how you can categorize all the different sound separation tasks that the community is working on. And so this is a 2D plot of the source class versus the number of source instances. So in terms of source class, speech is obviously a very important signal, and we can often observe multiple instances of speech in our daily lives. Music is another important signal, and there's a slight overlap with speech here because we can have singing voice, vocals in music. And then let's just call the rest of this 2D plane everything else. And this plot isn't really to scale because this everything else region contains just all the other sounds in the world. So it's very, very large. So given this plot, we can define different tasks by looking at different regions of the plot. So for example, singing voice separation is just separating singing voice from musical accompaniment. In this case, all musical accompaniment is kind of focused down into one source, and the singing voice is another source. Music separation, of course, is separating the distinct instruments from a piece of music. Speech denoising is a very important task where we're separating speech from non-speech. Recently the Merle folks proposed a slightly more general version of this where we're separating speech from music from everything else. And of course, speech separation is the cocktail party problem, separating overlapping talkers from each other. And this is usually studied only for 2 or 3 speakers, but there's work on scaling this up to having mixtures of more speakers at once. And so a task that we proposed a couple years ago now is one that can actually cover this entire space, where we want to separate all sounds of any class, no matter how many instances of them are present in a mixture. And we call this task universal sound separation. We think this is good because it covers this whole space of sounds that you would want to separate out from mixtures. The way that sound separation is usually done is with supervised training. So I was just going to quickly review that. And so in supervised training, we usually have isolated data sets of the sources of interest. So in this case, we have a bucket of plain speech and a bucket of non-speech data. We create synthetic mixtures of instances from these data sets. We run them through a separation model, which produces, in this case, an estimated speech output and an estimated noise output. And we compute a loss between the references and the estimates. So in this case, we know exactly in which order we want the sources to come out of our separation model. For tasks like speech separation, where we have multiple instances of the same class of sound present, or we don't really know in what order the sources should come out, permutation-invariant training, or PIT, has been a very popular and effective approach for this. And so we proceed as before. We make synthetic mixtures from our isolated clean source data. The model produces some number of estimated sources. And then we optimize some loss function between each of the reference sources and the estimates through a permutation matrix. And so we minimize the loss with respect to the permutation matrix P. And when we find the minimum loss, we take a step on that to do gradient descent for the separation model parameters. And supervised training has been really successful for, at least for narrow tasks, according to this sort of 2D visualization of the possible separation tasks. And so this is a plot from papers with code for the WSJ02 mix dataset, which is separating 2 speakers. And we started out at about 12 dB in terms of scale invariant SNR improvement in 2016. And these days we're up to, I think it's 22.3 dB. So we've made a lot of progress on this dataset. Of course, this task is quite narrow. It is only occupying, a small region in this in the whole space of possible tasks. And furthermore, this data set in particular, the speakers fully overlap, which is a mismatch from realistic speech mixtures like conversations. It's got a lower sampling rate, doesn't have any reverberation, and so it's sort of a limited task. And so now I want you to imagine that you're on vacation in Cambodia, and you take some video and you bring it home, and you'd really like to separate all the sounds from this recording you took. So I want you to think about all the different sounds that you'll hear in this scene, and how we can train a separation model for this. So I'll just play this.
Now I know we've got a lot of video of this place, but I mean, come on. Look at that.
Okay, you want to have pictures taken. 저기 그 무대구나. Group picture before you leave.
So this is a sound scene where we have a lot of different sources going on. We have multiple speech sources at different distances and different levels of reverberation. We have footsteps. We have this environmental noise. There's this funny rattling bell sound that I don't even quite know what to call. And so if we wanted to train a supervised model for this kind of setup, we would need to gather isolated data for all the possible sources of interest. The speech, both near and distant with the right reverberation, footsteps, wind, this funny rattling bell sound. And once we had all that isolated data, we could create synthetic mixtures. But just adding these sources together probably wouldn't generalize to the real world data, because there are a lot of complicated acoustics that we would need to try to match. We'd want to try to match the co-occurrence of classes and their overlap. And so this could actually start to get a little complicated, and there would be a lot of engineering involved. And actually in our initial universal separation papers, this is what we did. We took a big sound effects data set and we mixed together sounds from that and trained a network to separate those. But of course, this didn't end up generalizing all that well to real mixtures. So like I was saying, it would take a lot of engineering effort to build a supervised data set for these real world domains. And as I mentioned, real world data has a lot of complicated acoustic effects, a few of which are illustrated on this slide. And even though the supervised data is providing a very strong learning signal by giving a network isolated sources to learn on, we're inevitably the amount of data that we can actually use to train these models is going to be limited. And so these supervised approaches just are not going to scale to this universal separation task. Now, what if we could actually learn to separate from raw audio mixtures. So of course, we're not going to have any more isolated single source data for that stronger learning signal, but we are going to be able to exactly match the distribution of all these acoustic effects and the co-occurrence and overlap of sound types. And we can have basically unlimited training data that's totally open domain, only limited by our ability to record or find enough of it. And so this is where unsupervised sound separation comes in, which we define as being able to learn to separate sounds from raw mixtures with no access at all to isolated single source data. So let me describe our approach for unsupervised sound separation, which we call mixture-invariant training, or MixIT. And so it has some similarities with PIT, but also some key differences. So first of all, we take two raw mixtures, mix them together to make a mixture of mixtures, or a MOM, run that through a separation model to produce some number of estimated sources. And then instead of optimizing a permutation matrix, we optimize a mixing matrix, A. And so this is a binary matrix where the columns sum to 1. It's 2 by M, where M is the number of output sources. And just like in PIT, we find the mixing matrix that minimizes this loss, and then we use that minimum loss value to take a gradient step on the network parameters. And so we can draw some contrast with PIT. So PIT's on the top, MixIT's on the bottom. So with MixIT, the input to the model is a mixture of mixtures, whereas in PIT, it's just a single mixture. PIT is optimizing over M by M permutation matrices, whereas MixIT is optimizing over these 2 by M mixing matrices. And then in PIT, of course, we're using isolated sources as references. In MixIT, we're actually using just raw mixtures as references. So we sort of get that same discriminative signal by optimizing on these waveforms. So with that said, I now want to tell you about a few of the applications we've used unsupervised separation for. So this is an outline of the rest of my talk. So I'll start with talking about where we've applied unsupervised separation to a domain that really has no isolated source data. This is bird bioacoustics. Then I'll talk about how we can adapt supervised models on real domain data, particular the domain of meeting room recordings. Then I want to talk about universal separation, training on everything and separating anything. And finally, talk about our audiovisual model called AudioScope, which unsupervised separation actually enables and allows us to train unsupervised on video data. And I'll conclude with some future directions for unsupervised separation. So let's talk about the domain of bioacoustics first. And I just wanted to mention that my colleague at Google, Tom Denton, was a great collaborator for this project, and he organizes a lot of bird classification challenges. So I'm really grateful to him. So when we're in the forest, audio is a great way to study wildlife. Obviously, trees are opaque, and its vision isn't really going to get us very far here, but sound carries through the forest, and it can be very dense though. So let's listen to an example recording. So as you can hear, this is a very dense recording. There's a lot going on, but there's a lot of important sounds here that we can use for ecology to understand food sources and predators. And so studying this kind of audio and being able to automatically classify it is very useful. And so there are these autonomous recording units that are placed all around in the forest. They're recording thousands of hours of audio. And of course, thousands of hours of audio is very difficult to analyze for expert listeners. So if we can have automatic methods that work well for this amount of data, then that would be really useful. And so the question we had here is whether separating those dense mixtures first and then classifying could give us improvements in terms of classification. And so the idea here is that we take some input, we separate it, we run each of the separated sounds through a classifier. We also run the input through the classifier, and then to make predictions, we just take the max over the logits. And so in this case in particular, we're focusing on bird species prediction. So we were enabled to do this by getting a lot of data from some other great collaborators. So for example, the training data for our separation classification models comes from Xenocanto, which is this big public collection of bird recordings from around the world. There's also the Macaulay Library, which is a giant animal audio collection from Cornell. To evaluator classification models, there are these data sets taken in various places in the United States, Caples, High Sierras, and Sapsucker Woods. And we're really grateful to Mary Clapp and her team for providing annotations of this, of the California data, and also to the Cornell Lab of Ornithology. So if we want to train a separation model for birds, of course, we don't have isolated recordings. And so we can't train a supervised model for this. It would be infeasible to have every species of bird come into the studio and record itself in isolation. And so, of course, the solution here is to do unsupervised separation using MixIT. So we trained up some models with MixIT, and one question we had was whether just training on a bunch of open domain data from AudioSet, how that would compare with training on the matched bird data from Xenocanto. And so, interestingly, training on Xenocanto works a lot better than training on the AudioSet data. And so this might suggest that, you know, AudioSet doesn't actually contain a lot of birdsong. And so this is emphasizes the importance of training on data that matches your domain. The metric I'm measuring here is just scale invariant SNR improvement for reconstructed mixtures. So if we separate and then take the oracle assignment of sources to the two reference mixtures, then we just measure the SI-SNR improvement. And this is a pretty good proxy for separation quality. And I'll talk about this more a little bit later. In terms of classification, we got some slight improvements by separating and then classifying on this data set. We measured a number of classification metrics. In this case, I'm just showing one, which is label weighted, label ranking, average precision, LOLRAP. So if you look at the mixture only, that's just running a classifier on noisy mixture audio. The mixture and separated sources, that's doing what I mentioned earlier, where we run the classifier on each separated source and the input, and we take the max across the probabilities. So it's nice that we get some classification improvements here, but of course, the nice thing about training a separation model is that we can actually listen to the outputs of these separated birds. And so let's listen to a couple demos now. So in this video, first it will play the mixture, and then we'll listen to the separated sources, which will be color coded in the spectrogram. So let's go to listen. Let's listen to another example. And so these are two birds, and this is a particularly challenging example because these birds overlap almost completely in frequency, and so the only cue to be able to separate them is their different rhythms. So let's give this a listen. So we think that this is a particularly impressive result for the model. And so just to give some qualitative impression of why separation improves classification, this is showing the logit values for these different bird species that are present in the recording. We classify from the mixture on the top versus the separated sources on the bottom, and basically just showing that the logits increase in value for the separated sources. This is another example where we have a very distant bird with a lot of stationary wind noise. This thing is a high Sierras example. And so our model is able to, denoise single birds, and also the logit value also increases. So this is improving the classification. Let me talk about a different domain now. In particular, meeting room recordings. And I should mention this was an intern project by Ashwin Savaraman last summer, or summer before last. Our target domain data that we chose here is the AMI corpus, and this is actually a really nice data set to for this particular domain. So it's 100 hours of meeting room recordings. We have 3 different meeting rooms with different speakers and microphone configurations. This also has synchronized far field mic arrays and close talking headsets. And it's really a challenging data set. So there's a lot of sensor noise in the microphones. There's all kinds of different background noise, like air conditioning, rustling, fingers tapping. Sometimes you can hear traffic going by outside. And the speech itself is completely natural. So there's a lot of overlap. There's laughter and disfluencies. And so what we wanted to study here was how well supervised data would work on this, and if we could use unsupervised methods to adapt those supervised models. So for our supervised data, we chose to use Liber2Mix, and in particular a reverberant version, because we know this meeting room data is reverberant. Of course, we have the AMI corpus data, which is our unsupervised in-domain natural mixtures, and there's tens of hours per meeting room for this. And then we also use AudioSet as a just completely open domain unsupervised data set, and that's large. That's 5,800 hours. So in our setup, we're going to train a separation model with both supervised and unsupervised data. The fully supervised setup, we're going to use PIT. And so the model actually has 8 outputs. We're going to use PIT between the best 2 of those 8 outputs and the 2 references. So these are the isolated speech references here. For MixIT, we are going to make mixtures of mixtures for the AMI data and train that with MixIT. And we'll also consider a semi-supervised setup where we train the model on both supervised mixtures and unsupervised mixtures. And then where the AudioSet data comes in is we will pre-train the separation model on AudioSet with MixIT. Just to mention the network architecture that we use, and this is actually the network architecture we use in throughout this talk. This has been kind of our default network architecture for a couple of years now, which we call the TDCN++. This is essentially a COM-TASNet masking model with a few improvements. In particular, we just add some additional residual connections. We use feature-wise layer norm instead of global layer norm, and we also use a learnable scaling parameter after each layer. This helps with convergence during training. And just like COM-TASNet, this is just repeating super blocks of dilated convolutions. And then we use either a learned basis or an STFT. And both of these can work well. Some work better for other domains, but we generally use those. Anyways, one other thing I want to mention is we use this mixture consistency block at the end. What this does is it takes initial estimates from the network and it projects them such that they add up exactly to the input waveform. We've found this to be a useful constraint on separation models. To do some evaluation on this AMI task, we actually built a synthetic data set that would allow us to compute objective metrics like scale invariant SNR and PESC. We constructed this, or we were able to construct this because the AMI corpus has very detailed annotations where so we can identify all the single speaker regions, And then we use a linear time invariant filter to filter the headset to the distant microphone. So this can give us, isolated reverberant utterances that we can then mix together. Using the overlap statistics we measure from the annotations, we then sample overlaps and so that we can match the overlap in AMI. So here are some results. SI, SNR is on the left, and results of a listening test using Mushra are on the right for the synthetic AMI data. And so the first thing to notice here is that the purely supervised model is very mismatched. It's barely improving, if at all, on in terms of SI, SNR, and in terms of the listening test, it's essentially equivalent to doing no processing at all. Unsupervised training works very well here, either training on AMI with MixIT or on AudioSet with MixIT. The one interesting thing to notice here is that training on only tens of hours of AMI, which is completely matched to our target domain, works about as well as training on thousands of hours of open domain AudioSet. And what works best is doing a semi-supervised setup where we're using both this, mismatched supervised data and the matched unsupervised data. So that supervised data is, providing some stronger learning signal by giving the network isolated speech to look at, whereas the unsupervised data can help the separation model adapt. We also did a listening test on real AMI data, and again, in this case, the semi-supervised model works the best, and it's starting to approach the Oracle performance, which is just giving the isolated filtered headset. So let me play a quick demo here. So I'll just go through these in order. So we'll listen to a distant mic, and then the headset for our target speaker, the filtered headset, and then an estimate from the supervised model and estimate from the semi-supervised model.
Again, yeah. And I get to do another fantastic PowerPoint presentation. Again, and I get to do another fantastic PowerPoint presentation. Again, and I get to do another fantastic PowerPoint presentation. Again, and I get to do another fantastic PowerPoint presentation. Again, and I get to do another fantastic PowerPoint presentation.
So you can hear the semi-supervised model is producing better sounding outputs for that speaker. All right. All right. So third topic, universal separation. So as I was talking about earlier, we proposed this task of universal separation a couple years ago, and it spans this sort of entire space of possible separation tasks you would want to do. Like I said, we took some supervised approaches to this initially. A part of that was creating the free universal sound separation, or FUS dataset. We did this as part of the DCASE 2020 Task 4. And so this consists of it's supervised mixtures where the mixtures contain 1 to 4 sources, and we draw the data from 367 classes from the FSD50K dataset. So this is all open domain and public domain data. We get 16 hours of isolated training source data, and we generally use this as a evaluation data set for universal separation, as well as a supervised baseline for unsupervised models. One other data set we have ended up using a lot is the Yahoo Flickr Creative Commons 100 million, YSCC 100M. And this consists of 800,000 videos, which is equivalent to thousands of hours of, these are just real in the wild videos from Flickr, all with Creative Commons licenses. And so if we train a MixIT model on this, this lets us scale up orders of magnitude over FUS. So our training data for YFCC 100M has 1600 hours, which is 100 times the 16 hours of source data we have in FUS. So let's listen to a demo of a MixIT model trained on YFCC, and we'll run it on the same audio from that temple video I showed you earlier.
Okay, you want to have pictures taken. 저게 그 무대구나. Group picture.
So this separates out different speakers.
Okay, you want to have pictures taken with the background. This group picture. 저게 그 무대구나. Group picture.
As well as non-speech sounds like footsteps. And this funny rattling bell sound. And there's a little bit of speech at the end of that one. So it's not always perfect, and sometimes sources get grouped together, but generally it's doing a pretty good job on this in the wild data. So to measure performance of these models, as I've been mentioning, we use scale invariant SNR. There's a few specific metrics we use to measure the performance of these universal separation models. And I'll just talk about those briefly. So the first is MSI, which is multi-source SI-SNR improvement. And so this is the standard SI-SNR improvement we measure on separation tasks. So how well does the model separate multiple sources from each other? We also use this 1S measure. And so this is measuring a separation model's ability to handle single source inputs. So the idea here is if we feed a single source to the separation model, does it reconstruct that single source on one of its outputs? And we just measure the absolute SI-SNR for that. And finally, I mentioned this metric earlier. So this is what we call our mommy score. So this is just the SI-SNR improvement for reconstructing reference mixtures. So if you create a mixture of mixtures with two reference mixtures, feed that to a model, and then do the Oracle MixIT assignment from the separated sources to the reference mixtures, and measure the SI-SNR improvement. That's what this mommy score is. And this is the only measure we can actually compute on this unsupervised data where we don't have reference sources. It does correlate with MSI, that multi-source improvement that's run on isolated sources, but it's not a perfect correlation. But it's at least something we can measure that gives some indication of the separation quality. So just looking at some results, we can compare supervised training on FUS to unsupervised training on YFCC. And what you can see is that even though the supervised FUS model, it's getting very good 1S and MSI scores, it's doing very poorly on a YFCC 100M eval. So it's really not generalizing well to the real data. On the other hand, the unsupervised model is doing quite well on the open domain matched. It's matched data in this case, but the 1S performance, the single source reconstruction performance of the model degrades. And so this is kind of a problem with MixIT. And then note that the unsupervised model actually gets comparable multi-source separation to the supervised model. Now, scaling up the number of sources of a separation model is, obviously a useful thing to do to generalize to real world mixtures that have a lot of sources. And it's nice to increase the number of output sources because we are feeding the model mixtures of mixtures after all. And so, it's going to be seeing mixtures that have twice the number of sources than real single mixtures. So if you do exhaustive MixIT, searching over all possible mixing matrices, this is pretty expensive. It's O of 2 to the m times t, where t is your number of audio samples. And so we came up with an efficient version of this that we call efficient MixIT. And the idea is you just solve a least squares problem between your reference mixtures and the estimated sources. You take that solution and you can just project it to the nearest valid mixing matrix just by taking the max element over the column, set that to 1, and set the others to 0. And this helps us scale up the number of sources for MixIT models. And so on this plot, this black line is showing the point at which we empirically observed out of memory errors training with training MixIT models. So that's m equals 9 is sort of the limit. And this orange line at the bottom, that's efficient MixIT. So you can see it goes up to 16, and we could just keep on going if we wanted to. When you increase the number of output sources for an unsupervised model, then MixIT starts to over-separate more and more. Earlier, we saw that 1S performance went down just for the 4-output model. And it gets even worse when you have more outputs. And so what we found is putting some regularization on the output of the model is useful here. In particular, it's a sparsity loss on the powers of the separated sources, just a L1 over L2. And so the result here, if we train a 16 output model on FUS, we actually get even worse performance on YFCC 100M with, actually a little bit better performance on 1S and MSI. If we go from an M equals 16 model trained on YFCC and then we add sparsity, then we can actually greatly improve both the 1S and the MSI performance. Although we get a bit of a degradation in the MAMI score on YFCC, just because the model now doesn't have as much flexibility to use its 16 outputs to model all the sources in the reference mixtures. So then one other thing I wanted to mention. How am I doing on time, by the way? Okay, I might go through this very quickly then. So if you have data like AudioSet where you have weak labels for the sound classes and the mixtures, you can compute some classification losses. And the basic idea is that you can run each of the sources through a classifier, you get a posterior over the sources, and then you can use the MixIT assignments to combine those posteriors for the two mixtures to match the weak labels that you have at the input. I won't go into the details of the math here, but basically you can take an OR or an XOR of those posteriors to aggregate them, and then you can just use a cross-entropy loss. And what happens here is that the model learns to focus certain source classes into specific outputs. So I'll play this demo real quick. So the model separates this background sound. But then it kind of pulls apart the speech. So there's this bit where people are talking at the end. And there's this guy yelling in another of the output sources. And so the classification regularized model learns to put all the speech sources in one output. So this is sort of an instance of being able to control the output of these separation models a little bit. Okay, the last thing I want to mention is our audiovisual separation model, which we call AudioScope. So this is work by another one of our interns, Ephemios Zenas. And so the basic task here is, let's say we have a microphone and a camera, and we want to enhance only the sounds of objects that we can see on screen. So in this case, we want to isolate the sound of the person in the red shirt and the dog barking from the person in the green shirt and the sound of wind. So MixIT actually enables a really nice way of doing this in an unsupervised way. So here's how it works. Just like MixIT, we create a MOM. And in this case, one of the mixtures, we have a corresponding video soundtrack. So we do an unconstrained separation of this mixture audio. This is actually pretty different from a lot of the audiovisual separation approaches, which often condition a separation network on video frames. So in this case, we are just doing an unconstrained separation on audio. We compute embeddings for each of the sources in the video frames. We do some audio-visual attention, and then this gives us a classifier. For each source, we get some probability that originates from an on-screen object. These probabilities can be used as mixing weights to compute an on-screen estimate. And MixIT actually enables us to train this unsupervised. We can take the assignments we get from MixIT. We know that any sources that map to this random soundtrack are definitely off-screen. For the ones that map to our video soundtrack, we can just use a multiple instance loss to say, oh, some of these might be on screen, some of these might not be. And this is a very effective recipe. And so we've had a couple versions of this model. We started out with our AudioScope V1 model. So we can go from 2.5 dB up to almost 6 dB. AudioScope V2, we improved the audiovisual attention architectures for our model, and that gives us an additional boost. And those models were all at 1 frame per second for the video. So if we increase the video frame rate, we also get a further boost in performance. So let me play a little demo of what AudioScope can do. And so I will play the unprocessed first and then the processed. And so try to listen in the unprocessed for what sound should be removed based on whether you can, see an object on screen making those sounds. So, as you can see from those, we can handle, all types of different sounds, music and speech and rattling and background noise. And so we're pretty excited that unsupervised separation can enable this sort of audio-visual processing. Okay, so future directions. There are some limitations of MixIT, and I've mentioned a few of these throughout the talk. So, one is that MixIT uses mixtures at its input, but in the real world, we want to separate single mixtures. So that's inherently a mismatch. MixIT can also over-separate things, as we saw, when you increase the number of output sources. And so regularization is required, and there may be other methods that are better at doing this. And then one other thing we've noticed is that for certain types of domains, especially music, MixIT can actually under-separate. So if the sources are correlated, then it can kind of keep them together. And let me play just a quick demo of that. I hope that's not too loud. So it does a pretty good job at separating out the guitar. But it keeps the bass and drums together. Coming up with methods to prevent this sort of under separation are going to be necessary. Oh, I'm sorry. So of course, I've only talked about applying MixIT to audio. There are a lot of other domains with time series where MixIT could be really useful, like underwater bioacoustics or biosignals like EEG, or maybe even seismic data separating out tectonics from passing trucks. And finally, there's been a lot of talk about big foundation models lately. Existing foundation models don't really guarantee good disentangling representations across sources, but MixIT, of course, is a great tool for learning on lots of data in terms of disentangling across sources. And then also just combining MixIT with generative models is another really interesting direction. All the results I've shown have just been with deterministic masking-based networks. So I think there's a lot of potential in doing more generative things with unsupervised separation. Okay, so that's it. I'd be happy to take any questions if we have time. Thanks so much.
Thank you so much, Scott, for being here to the talk. I have many questions, but if I can only ask one, I was going to ask, how do you contrast, like the pros and cons of these types of approaches where at the end of the day, there is still like this type of parameter of one way or the other, versus like, query-based separation where you just kind of like completely embedding, and you can imagine over 80 bajillion hours of data that you often would complete embeddings of symbols working in the top instantly. So
That's a great question. So the question was compare and contrast conditional separation methods where we can condition a separation model on some additional information versus this approach of separating everything into M sources where you have to choose M. With the conditional separation, it's definitely like a pro of it is that it results in sort of like more efficient and focused networks, right? Because they really just have, say, two outputs, one output that is the desired audio that your conditioning signal is giving you, and the other one's just the residual. So that's nice. But kind of a drawback is you have to carefully engineer your embedding signals, your conditional embeddings, depending on what you want to do. I've also collaborated with some folks at Google doing these either audio or text conditioned models. And so for those, you have to kind of know what you want to separate ahead of time. So if you want to separate out the sounds of all dogs from your recordings, you have to find a good representative like piece of audio of a dog barking and use that as conditioning. It's a little easier with text, but still you when you're given a recording, you don't really know what's in that recording until you really listen to it. And so that's where these sort of unconditioned separation models trained with MixIT can come in, where you can separate any mixture and then sort of study what sources are in it, and then maybe choose what to keep or throw away. So what's that? Oh yeah, that's a great point too. So yeah, and also for like multiple instance data, conditioning models might struggle a little bit. Like if you have multiple people talking, and if you condition it with speech, it's just going to separate out the multiple people talking. It's not going to separate out the individual speakers. So yeah, those are a few pros and cons. Thanks. That's a great question. Yeah.
You were able to separate the noise based on the
Mhm.
and then even there was the basic one. Can you talk a little bit about what's the difference?
Oh yeah, that's a great question. Yeah, so the question was, there was the demo of separating birds, and those are sort of overlapping in rhythm, and then there was the example of music where it couldn't separate, say, like the bass from the drums. So yeah, I think in this case, it's kind of about the independence of sources. Like these birds are not necessarily like synchronized with each other or really correlated with each other. It's different species of birds kind of calling to each other, trying to fit their calls in the channel. That you can think of it as like a communication channel where they're all trying to compete for bandwidth. Whereas in music, the sources are trying to be like synchronized and to blend together to kind of create one source and create one source with a certain timbre. So I think that's kind of the difference. It's all about like the independence of the sources.
One last question, then. Thank you for the great talk. So I have a question regarding when you practice separate out these sounds where you don't know what how much have you any analysis where if the two sources are very very close to each other in let's say like can it separate out, or are those the cases where the MixIT model is not able to capture the And where is the negative? How do you see if somebody wants to improve upon the model? What are the different scenarios?
Yeah, that's a great question. So the question is, maybe if I could restate it, hopefully I'll do it accurately. Like, are there sources that are inseparable? And like, how could we deal with those? And what are some potential techniques for dealing with that? So yeah, well, one example is like stationary noise. So if you have multiple sources of stationary noise, that's actually very hard to separate because those are like stochastic things. They don't really have any deterministic structure to lock onto. So I think that's one instance. So, like more stochastic signals can be a problem for things like MixIT. In terms of methods to solve that, I don't know if I have any great ideas, but that's one instance. And of course, the music case is another one where you have sources that are really trying to blend together. And for that, it's also a good question. Like, how can we, really force the model, sort of peel these things apart? So yeah, I'm afraid I don't have any great suggestion, but I'm happy to talk about ideas. Thank you.
Let's thank Scott again.
Thanks.